Okay, so I thought for this occasion, because it's the two communities coming together here, so the quantum information people and the operator algebra people. I guess there are more operator algebras here, right? But anyway, so there will be some. I thought of to give an overview and look at some of the basic themes from both sides and try to speak a language that might, that I hope would address both. So my first part will be about something like that, 3 cultures of quantum theory and infinity. And the second part will then be about separated labs. So, as I said, I mean, the quantum information community already is a very mixed bag. Right? So you have physicists, you have computer scientists, you have mathematicians, and you have experimental physicists and some engineers and so on. So this is a very mixed group. And so you get used to talk to different kinds of people. And so one group you talk to are the computer scientists. And one of the characteristic features, I mean, I'm always talking about computer science within quantum theory, right? So as what happens when the computer scientist goes quantum, right? And one thing you will notice is that these people are very strict about doing everything in finite dimension. And so this is why I call this the item 1n, right? So if you're a physicist, as I'll come to that later, but that may be strange at first, but actually they have very good reasons to do so. So, for example, if you do theory of computation or also of communication, one of the things that you want to avoid, like the pest, is sneaking in an infinite resource. So if you allow yourself an infinite computation space, then you can solve all kinds of problems, but you sort of trivialize the problem of computation. For example, there was a paper where somebody had found a quantum algorithm to solve Diophantine equations, which we know is not recursively doable, right? So it's not a question of speed, just there's no algorithm for that. But the algorithm actually used an harmonic oscillator and basically trying out instances of your equation in various ranges of the spectrum of this oscillator. Now you have infinite space, so if one of them, from one of these regions you get a yes signal, you've solved your equation. So this is what I call sneaking in an infinite resource. And there's good reason to be very careful about this and totally avoid that. And this, of course, this becomes ingrained in the training of computer scientists, and they find it very strange that physicists are much more relaxed about infinity, right? So, so before actually discussing the next item, I would have a small interlude here. Going infinite dimensions, going infinite. And one possible setting in which to do this is what is now known under the keyword of generalized probabilistic theories, where you have a state space, convex state space, right? And well, what you do is, here's your state space. Should have a corner somewhere, maybe. And then you draw a cone to the rat, and the ordered vector space that you get for that is the typical thing that you use for states. Abstractly, this is called a base norm space, or a base normed ordered Banach space. For the observables, we get also a cone with the identity somewhere, and so this is an order unit space. And the basic observation that I want to make here is, so these spaces then also become infinite dimensional, right? When your Hilbert space goes infinite dimensional, the trace class becomes infinite dimensional and everything else. So these are, well, finite dimensional or non-reflexive. That is, the bidual is not the same space, right? And so this means that you have to make choices about whether you want to take your observables or your states as primary objects. And there are different ways to make those choices. So, for example, I wanted, that's also in the commutative case. So which is the space, which is the dual, right? So there's one possibility you take, for your observables, you take the continuous functions. Actually, I'm just repeating something that Adam Majewski said yesterday. And then the dual would be the space of measures on that compact Hausdorff space, right? But you could also take L1 of x with some measure and take its dual L infinity. And so the lines that I drew means that there's a canonical bilinear form that evaluates a measure or an integrated function with some observable. Right? So here are the states. And I'm drawing this to point out, there will be similar diagrams later, I'm drawing this to point out that there is a choice that you have to make. Actually, in this case, it's the choice of, this choice is measure theory, and this choice is topology, right? And they tell you different things about your physical system. So, so there is a choice to make. Actually, if you want a complete picture, maybe you would work with, let's say, an L infinity with some dense, weakly dense, of course, weakly dense C-star algebra of observables, or something like that, right? So this is the typical choice that you have to make, right? Okay, so let's go on with this. So let me just recall here, don't sneak in infinite resources. So the next level is the physicist. Well, actually most of physics, right? And physicists are quite happy to have an infinite dimensional Hilbert space. Could be infinite, but always separable. Right? And so this would be the culture 1 infinity. And okay, so let me see what I wanted to say about the physicist. Well, this diagram is evolving. Monty. Shit. Sorry. Fantastic machine. So you would have your good old bounded operators, and if you draw it like that, so on that side will always be the observables. There's the trace class. Of course, this space also has a dual. There's no special symbol for that. And the trace class also has a predual, which are the compact operators. So these are the compacts. Trace class. And here live the singular states. So one thing to notice about that kind of diagram is when you go to a dual space, you learn that you have the unit ball of your Banach space that you're looking at will be weakly compact. That's a Banach Alaoglu, right? So that also means that you have many extreme points. So in the measure theory case, means that you have many projections. Those are the extreme points of the unit interval that I drew there, right? So, and on the other side, you get pure states. So if you're thinking in terms of L1, then typically you don't have pure states if mu doesn't have any atoms, right? So if you have a measure on the unit interval, then there are no pure states in L1. So if you want to talk about pure states, and sometimes that is practical, because that's a good idealization for certain problems, then you'd better look at the appropriate duality. So it's typical that being a dual space comes with having many extreme points in the unit sphere, which we otherwise don't necessarily have. So in this case, the fact that the trace class is a dual space means that we have many pure states, right? So, yeah, okay. So let me just say many pure states. They generate the thing, right, by Neumann, right? So many pure states. Which is actually, will be a distinguishing feature relative to the next level, right? So the usual quantum mechanics that we know has this feature of having very many pure states. So I should maybe comment on the singular states. So probably you won't find them in physics textbooks, although they sometimes might come in handy. For example, so an example of a singular state, a state with sharp position. So this is very different. So this is just to, if you think of these improper kets that you find in physics textbooks, that is definitely not what I mean, because the norm of the x with itself is the value of the delta function at 0, which is very, very infinite, right? So this is not a state at all. But how do I get something like that? You take C of, let's say, R, look at this subalgebra of B of L2 of R. Now, on this space, you certainly have a state. On this subalgebra, you have a state that has sharp position. Just take the point evaluation, let's say, at 0. Right? Take the delta function here. And then do a Hahn-Banach extension. And there you go. You have a state on B of R, or B of H. And that will be an element out here. But we know that we cannot do this with a density operator, because they always have L1 densities. Right? So it can be, if you actually want to discuss this, states with sharp position, and that it might be useful to do that as some kind of an idealization, then why not use singular states? So they satisfy the uncertainty relation. So uncertainty relation is 0 times infinitely, which is true somehow, right? So it's a special case that you would have to add to that, right? So what this infinity actually means, and so first of all, how do we know there is such a state? Well, by the Hahn-Banach theorem, which means by a heavy use of the axiom of choice. So we cannot actually exhibit any such state on B of H, although we know it will have a good expectation value for anything that we write down. For example, for the interval, for a projection onto an interval of momentum. And because of this property that it's an eigenstate of position, it will give the same value to every element of the same length on the interval. So you conclude that whatever that state is, there will be many. This is not uniquely defined by this property. This extension is not unique. Whatever you take, which extension, it will have probability 0 for finding any finite momentum, which is kind of a good description of that infinity. Okay, so come back to that, right? Why not stay in Hilbert space? Well, let's say one infinity, the B of H point of view, is not so good for infinitely many degrees of freedom. So let me do another little interlude. Just to fix some terminology. I guess in this audience I hardly need to do, I'm not sure about this, but let me do it anyway. I'll try to be quick about it, right? So, so the typical picture there now generalizes to a von Neumann algebra, a C-star algebra, and its dual, right? So, but I mostly want to talk about the von Neumann algebra. So actually, this was one of the big problems in the early theory of operator algebras, to characterize those C-star algebras that could actually be the weakly closed subalgebras of B of H. And the answer is exactly those that have a pre-dual. Right? So this, the model here, the model for that, and actually an exhaustive set of models, is weakly closed. Well, actually, there are several operator topologies that you could use. Weakly closed in B of H. Anything that has that property and is a star algebra, and this is the norm closed part. Huh? So if you want to see, that's a basic distinction. And I wanted to mention briefly the types. So I was writing 1n and so on, that this is part of the, as most of you have probably realized, this is part of the classification of von Neumann algebra. So von Neumann had more types, and this was completely based on an equivalence relation of projections, which means that you can write one projection as V star V and the other projection as VV star with the same element of the algebra. Right? Now, whenever you do that, you can see that by just, even the physicists can do that by just looking at that, seeing that the trace of P is going to be the trace of Q. And for that, you don't need the trace on the Hilbert space, but any functional with trace-like properties, which you can abstractly define. So, so actually, the set of values is a good classification. So this is the basis of that classification, right? So, so type 1, then here you get, well, the natural numbers, or actually, because there's no overall factor for the trace specified for properties that you need, some fixed number times the integers, right? Or maybe a part of the integers from 0 to n, that would be type 1n. And if you have all the integers, it's type 1 infinity, and you know very well that this is the range of the trace on Hilbert space projections, right? So, so then the next is type 2. Then this set is either an interval or the whole positive axis. Well, yeah, it might include infinity, actually, okay? And the typical thing here is that every projection can be written as P1 plus P2, where P1 is equivalent to P2. So you can split every projection into two that have this, that are equivalent among themselves. So that means if for the value of the trace, whatever the value of the trace is, you can find another projection that has half the trace. And finally, we have type 3. And there, this set has only 2 points, namely 0 and infinity. And this has a similar property. So every projection can be written as P1 plus P2 with P equivalent to P1 and P equivalent to P2. Now, the only way something can be equivalent to its part is that it's infinite. These projections are called infinite, and those are infinite von Neumann algebras, and the lingo for that is type 3. So sorry for boring you with that. Okay, so let us continue tableau 2. Let us continue with this run of 3 cultures. So the next level that I want to look at is field theory. And here you actually run into larger von Neumann types than one. So, so the distinguishing feature here is that you have infinitely many degrees of freedom. So there are 2 principal examples that I want to mention. The first is by von Neumann, of course. And it is infinitely many qubits. Well, von Neumann wouldn't have said qubits, but that's exactly what he writes down, right? So this is a paper on infinite tensor products, and he discusses in detail actually this case. So let's say, infinitely many. Let me replace qubits by singlets, right? So I want entangled states also. So a singlet is a maximally entangled state of 2 qubits. So you have a 4-dimensional Hilbert space for each one of them. And now you want to do the infinite tensor product. That's kind of would probably be your first reflex also as a physicist. So how would you define that? Well, you know that for a tensor product, should contain tensor product vectors, and their scalar product, so there would be something like this. Should be the product of these scalar products, right? Now this is an infinite product. This infinity is the only important thing to notice. And that is intrinsically ill-defined. Right? This could be anything. There's no reason why these scalar products should be small or going to 0 or to 1 or anything. So if you just write it like this, you simply don't know what to do. And the reason is that you have infinite products of things that are not asymptotically 1. Actually, von Neumann's paper, he makes a tensor product by cleverly declaring the divergent scalar products to be 0. But that's another story. I don't want to go into that. Right? So von Neumann doesn't find it quite so as bad as I do. But there is a way out here. And the way out is actually the reason why you go from Hilbert spaces to algebras. So a better thing is to take the 4x4 matrices, let's say, and make an infinite tensor product of those. Now, in the same vein, the reason why that works is that you have a canonical element here that is very tensorable. The number 1 you can multiply infinitely often without anything bad happening, and the operator 1 as well, right? So you define this as closure of local observables. So local observables in such a string will be those that have the factor 1 everywhere, except infinitely many places. Well, this could be awfully many, but anyway, only infinitely many places. And you know exactly how to multiply such operators, so they make a nice C-star algebra. And you can make a closure of that, and this gives you the key word for that is the quasi-local algebra. Or let me write for emphasis C-star algebra. So we've moved into the realm of topology, this slope, right? So we can have M4 tensor infinity, call that maybe A. That's your C-star algebra. And this has a dual. And I won't say anything about this because this is wild. You don't really want to look at this guy, right? So all possible states on this object are a rather unwieldy thing, and it's also not what you really want, for example, if you want to describe infinitely many singlets. You have a state on each one of them. So here would be something that I call good states. And the good states in this case will be the product states arising from, first of all, it will be, singlet, the state here would be, let's say, omega something, right? So there is on any one of these local observables, and therefore on the closure, omega tensor n infinity is a good state, right? This actually describes what you mean. You want to describe a situation with infinitely many singlets, and therefore you fix that state everywhere, and then you can compute all the expectation values, and you make a GNS construction, right? So you make a GNS construction. And actually, the GNS Hilbert space that you get in this way is what von Neumann calls the incomplete tensor product. The incomplete tensor product is formed by a reference unit vector, which is a basis vector here. And now you can tensor things because almost all the factors will be equal to that fixed unit vector, your reference vector. And therefore, you can make sense of such products. So actually, the GNS construction for this guy is exactly the same as this incomplete tensor product construction, where you have a reference vector and you take the completion of the set of vectors that are different from the reference only in finitely many places. Then you can do your scalar products, and then you take a Hilbert space completion. That's the same thing, right? Okay, so here you get a nice von Neumann algebra, and now we have the situation that we have actually many von Neumann algebras. So we have a factor M2 tensor M2 for Alice. First singlet, right? And for Bob, second. And then we tensor that with, again. So these are the M4 factors that I talked about initially, for which I do the incomplete tensor product. And now I take all these guys together. So everything that belongs to Alice. And I take the reclosure of that, or the double commutant, which is the same and is indicated by these dashes, right? So this is what I call R1. And as it turns out, what you get when you do the same thing for Bob, you get the commutant of that. That is, this prime always means a commutant. That is the set of all operators which commute with a set on which I put the prime. So if that set is closed under adjoints, this is always a C-star algebra. Actually, it's always a von Neumann algebra. It's a weakly closed algebra, right? So we have two new versions of localization for Alice and Bob, and we'll go in that a bit more. But before that, I want to give the other example, which is algebraic Q of t. So if you have O in Minkowski space, I do not apologize for saying Minkowski instead of Minkowski, as seems to be the custom in the States. So O is in Minkowski space, an open set, and you associate to that the observables measurable in O. And if O1, there are two regions, this symbol means that they are space-like separated, that is, they're They have a light cone between them. They're space-like separated. That implies that A of O1 commutes with A of O2. That's sort of the one of the basic assumptions of this axiomatic algebraic quantum field theory, right? Again, you have many algebras that are all commute. It's a little bit like these M4s, and you have a good state. So the good state. Sorry? Yes. Well, yes. Basically, yeah. If you want to be, actually, there's a lot of subtleties there. So if you want to really have the simplest case is to take only double cones. That is intersections of a forward and a backward light cone. Otherwise, you can get some funny things. So let's take just double cones. But depending on the mood, they would try different things. But okay, so the good state here. Well, there's some more axioms. For example, an action of the Poincaré group of the space-time symmetries, and also that there should be a state that is invariant under that. And this is called the vacuum state. And then you play the same game. So you can do your GNS representation. You get C-star algebras in the representation. You take the von Neumann algebras generated by them, and they still commute, of course. So you get commuting nets of von Neumann algebras. In this case, it's actually important to take the bounded ones. The global structure is a tricky thing. You can talk to Peter Nikens about that. He's worked on what they call the super selection structure here, which is actually the structure of possible representations of this. So locally, it's pretty clear what the von Neumann algebras should be. Globally, not, because that depends on the behavior of the state at infinity. Okay, so field theory. Yes. So in both of these scenarios, you have the phenomenon of separated labs, right? So so this is about what I wanted to say about infinity. There's a lot more to be said, of course. But let me come to my part B, separated labs. So in von Neumann's example, there's an obvious thing here. You could take this von Neumann algebra and its commutant. This would be like Alice and Bob. So you would say that A and B are commuting von Neumann algebras. And so now more things can happen than can actually than you might anticipate from the separated lab scenario as it appears in quantum information, right? Where of course two commuting algebras, when they don't have a center, there will always be just tensor products of matrix algebras, nothing much happening, right? Still, there's a lot of interesting stuff to be learned about entanglement. So what do we learn here? So von Neumann's examples, and this is also true in the field theory example. The first surprise maybe is that there's many situations where you have no product states. So actually, that's false, but there are no normal product states. Now, normal product states in this von Neumann picture would be states that actually have a density operator in the overall Hilbert space, in this GNS space, right? So those are normal states on the algebra that is generated by A and B, and there are no products. So what happens to the notion of separability, right? So why are there no products? Well, the way this Hilbert space is constructed is that you start with infinitely many singlets, And the only modifications you do to that is operating essentially with finitely localized observables. So if you march down this chain, you will find unperturbed singlets, and they will never become a product, right? So you just have to go far enough along this direction. You could make this formally, right? And you will find that for the endomorphism that shifts you in this direction, every state actually converges to the original all singlet state, because the modifications that you make in the GNS construction based on local algebras will only modify the initial part of it, and further down the road, everything will look like a singlet, right? So this means that you have no normal product states between these two von Neumann algebras. There's no vector in Hilbert space that would be a product between these two. That's one of the really basic facts here. On the other hand, you can do something else. This is why I have to add the word normal. So you have this algebra that is generated by R1 and R1 prime. You know exactly what the algebraic rules are in that. So you just define a functional which is a product. And, well, then make a Hahn-Banach extension to B of H. What you get is, of course, a singular state, right? So, so exactly as in the case of a state with sharp precision, you can still make product states here, but they will be singular guys, which in physical terms would typically mean that they require an infinite investment of some resource, right? Energy or accuracy of some sort or so on. I mean, nobody believes that you can prepare sharp position. That means a point in the continuum, right? So even the best of physical measurements are good in 20 digits or so, but nothing like that. So it's talking about points in the continuum is a bit outlandish anyway. So anyway, this is a typical thing. There are no product states, and actually every normal state far enough down the road looks like a maximally entangled state. So this is what I call infinite one-shot entanglement. So you can do things in the type 1 scenario. You could do things like very, very highly entangled states, and you could even arrange that, let's say, the distillable entanglement is infinite, which means that I get sufficiently many copies out of that. I can get even more singlets out of it. Well, not just even more, but superlinearly many more. So this would mean that the distillable entanglement is infinite, which you can arrange, right? This is something entirely different. From a single copy of a system prepared in that state, if I just extract just a piece of the chain further down, I actually get an arbitrarily highly entangled state, right? So this is what I mean by one shot. You don't have to go through a distillation process to get this entanglement. You just have to project somewhere down here, right? Down the road. So this is also true in algebraic quantum field theory, and here I have to name my co-author, which is Stephen Summers. And we did that in increasing generality from the early 80s on. So this is kind of a long time ago. Okay, so the vacuum actually is such a state of infinite one-shot entanglement when the regions actually touch. So the von Neumann algebra that is associated with a wedge-like region, so where they come as close as possible, but are still space-like separated, the von Neumann algebras for that, by the usual axioms of these algebraic quantum field theorists, are type 3 one-factors, and they have the same property that any state between the algebra and its dual is going to be maximally entangled. I have 5 minutes, right? Yes, so let me erase one of these. Descente. They are clearly labeled, but the labels have faded a little bit since the time of Hermite. Okay, so two things, apart from this non-existence of separable states, separable normal states, one cautionary remark. So this new kind of separated labs are not as independent as what you're used to. For example, in the quantum information style separated lab scenario, they're really far apart, and Alice can do whatever she pleases, which includes ditching her system and preparing a new one. If you do that here, you end up with a product state, and they don't exist. So Alice depolarizing is forbidden. That is, it's forbidden because it's a singular operation. Well, okay, we can discuss that maybe, how much we have to forbid actually, but it's if you talk separated labs for Neumann algebra language, the natural thing is to go for the normal state and take seriously that there is a distinction between normal and singular, right? So in that sense, it's forbidden. So another caution. So the algebraic quantum field theory does not capture the notion of local operations. This is a curious thing. I used to think so for a long time. Actually, the work with Stephen Summers that is now covered on the vacuum was completely in the framework of algebraic quantum field theory, because they have exactly what you need to discuss entanglement in relativistic terms, right? So the locality here is really relativistic locality. You have a fully quantum theory there, and that's a good setting in which to discuss Bell inequalities, right? So actually we showed that Bell inequality is sort of also maximally violated always, which is not a surprise when you see what I told you. Okay, so local operations are of course the lifeblood of this whole notion of separated labs. Those are the operations that can Alice do without Bob being able to interfere. Now, one possible rendering of this notion in this algebraic context would be to say that these are operations that, well, first of all, you want that every operation has a meaning for the whole system. So it should be a channel that has an extension to the environment B of H that covers everything here, right? So they should be extendable, so there should be Krauss operators, and the natural assumption is actually that the Krauss operators come from the local algebra. That on first sight, this is a good notion of local operation, but then you come in problems when you start multiplying various such operations, and here's a basic situation that goes bad. So somebody does something in this space-time region. This is now a space-time diagram with time and space. And now we have a local region here and a local region there. So if the regions are like that, so the middle region sort of straddles the light cone, then you can actually signal from here to there. And the reason is very simple, and it's immediate to any quantum information person, that the algebraic closure of we're talking about local algebras, and the algebraic closure makes closures of operators that come from this end of the region and some that come from that end of the region. And those can actually be used to install a signaling process. So the local operations of quantum field theory allow you too much. They allow you signaling between different parts of O, superluminal signal between parts of O, and it would be an interesting project to come to grips with that. Maybe algebras are the wrong thing, right? I have never understood why they want local C-star algebras or for Neumann algebras, apart from the obvious fact that you know more about those. Okay, so I'm about halfway through. So let me just say two sentences. Things that I had on my list were distinction between two different kinds of infinite resources. We had an infinite entanglement resource also. Think of this as an entanglement bank from which you can get as much as you want. Alice and Bob go to the different branches. So this is one notion, entanglement serving, I would call it. This requires, in some sense, the cooperation of the bank. The other part that many of you here are interested in would be embezzling. And that actually means that you have an inner operation on one side. You also want this to be without communication. And I would have some remarks about that. So actually, the universal best entanglement bank that you could think of will give you as many singlets as you want without actually changing. Now, I've drawn the state for that, right? Infinitely many singlets is just that, right? You kick out as many as the customer wants, and you have a Hilbert's Hotel sort of situation that the rest stays the same. Now, for embezzlement, this is also possible, but if you want inner operations, the only thing that you could embezzle from such a state would be a tracial state, and you might want something else. And therefore, there's another universal object from which you could, which we call the universal embezzling algebra. That is the hyperfinite 3-1 factor, which has just the right property for that. This is based on papers of Magdalena with Uwe Hagerup and some other things. My co-author on that is Volker Scholz. And with that, I close.